Ethics. So thank you, Manos. Go on.
Thank you, Mario. Thank you very much for the introduction. And I'd like to welcome you again to the RPW Virtual School. My name is Emmanouil Kioupakis from University of Michigan. And I would like to tell you about the techniques we use to study phonon-assisted optical properties using EPW and the Electron-Phonon coupling methods. I want to start the motivation by talking about the optical properties of silicon. So what you see here is the band structure of silicon, where you let me choose a color. All right. Oh, sorry. Where you see here's the band structure, and when electrons in materials interact with photons, they get energy from the photons, but they get very little momentum, right? So electrons get excited vertically in this energy momentum diagram. And so this process is very well understood today using first principles techniques. As you can see, here's the diaphragm experiment for the epsilon2, the imaginary part of the electric function. The data points. If you do GW corrections without excitons yet, you see that you do get the right peak positions, the right band gap. And if you go one more step, you include excitons, you see you get an excellent agreement, even with the peak heights and the shape of the spectra as well. And not only that, but you can also include the broadening due to electron-phonon interaction at various temperatures. And you can see how you can also capture the shape of the curves at various temperatures. This is from the work of Marini from 2008. So as you can tell, the direct part of the optical spectrum of silicon is very well understood. The challenge is when we want to talk about the visible part of the spectrum, because this is crucial for silicon solar cells. Silicon solar cells would not work if you did not have phonons. The reason is that the band gap of silicon is indirect. The minimum direct band gap is 3.4 electron volts, which means that for this direct process to happen, you need ultraviolet photons. Everything you see here happens for energies above 3.4 electron volts. So that's not where the solar spectrum is. The majority is in the visible. And in order to have visible absorption in the spectral region between the indirect gaps at 1.2 eV and the direct gap at 3.4, you need phonons. You need both the energy from the photon and the momentum from a phonon to enable this indirect transition across the indirect gap. And that's what I'd like to talk to you about today. By the way, just a reminder that this is a school, so please feel free to answer questions. I will keep monitoring the Q&A as you ask your questions. I'll be happy to answer them on the spot as we go. But also, I'd like to also ask the co-organizers if they could please answer any questions that come up during the talk. So please, this is meant to be an interactive, and if we're in person, I would try to make it more interactive, but let's do the best we can in this format. All right, so the goal here is to understand these optical processes that do involve the assistance of a phonon. Before we talk about the phonon-assisted processes, I'm going to take some time to talk about direct optical processes. And the question we're trying to find is, how do we calculate properties involved in linear optics? We won't talk about linear optics yet today, but we'll focus on linear optics. Quantities such as the refractive index of material with a symbol n that dictates how light refracts between our material or gets reflected from the surface. Another coefficient is the absorption coefficient, which defines the loss. So if you shine a beam into a material, you see that there's an exponential decay of the intensity as the light propagates to the material. And the coefficient that describes the decay is the absorption coefficient in units of inverse length. It tells you how deep in the material the light can penetrate before it gets absorbed. So for a strong absorber, the absorption coefficient alpha takes in the range of 10 to the 5 to the 6 inverse centimeters, which means that light gets absorbed in the first 100 nanometers or so in a strong absorber. Just to put things into perspective. All right, so our goal here is how do we calculate these properties, the refractive index, the absorption coefficient, using this starting from density functional theory, and the only information being the atomic numbers. All right, so first of all, let's couple these parameters together. So in optics, we use what we call the complex refractive index to describe the combined effects of refraction and absorption. The real part is the usual refractive index. The imaginary part describes the absorption, the kappa coefficient. And this the complex refractive index relates to the complex dielectric function, which again has two parts, the real and the imaginary. By convention, we call them epsilon and epsilon2. Again, the real part describes refraction, the imaginary part describes absorption. And the way the two of them are connected are through these equations that you see here. squares and square roots. Otherwise, it's a very simple expression to go from one set of coefficients to the other. And finally, to get the absorption coefficient that we spelled this in the first slide, we need also to invoke the absorbance and the from kappa, also need to invoke the wavelength and some geometric factors. All right, so all of them are connected to each other. So that's why here we'll focus on the epsilon and epsilon2 and show how to once you have epsilon2, you can find the others. All right, so let me just make you show a very simple example of why phonons are important. All right, so for actually upon Samuel's discussion, here's an equation that describes the semi-classical motion of electrons in the material. This is Newton's law. So here's the mass times acceleration is equal to the force applied by the external electric field minus the scattering term. This acts like a friction term. It's opposite to the velocity, as you see here. It has a negative sign. And the scattering time tau describes this, quantifies this friction. All right, how often does the electron scatter and its direction gets randomized. And if you solve this to find the conductivity, you find the Drude equation for the electroconductivity, charge density of the electrons, charge of electron square, scattering time tau over the effective mass. That's the response for a static field. But now if you have light, your field is oscillating, and you can follow the same steps for an oscillating field here, and you can extract the absorption coefficient for a metal. Now this is not an interband process, because you go from the valence to the conduction band. This is an intraband process. As you see, it involves quantities again, like the density of electrons, the refractive index, the effective mass, and the scattering time tau. So you see right away that if you don't have scattering, if you don't have electron-phonon coupling, the tau would be infinity and the absorption would be 0. Okay, so you need scattering for electrons in a metal to absorb light. That's generally true. A free electron in empty space can't absorb a photon. There is no way that you have an electron plus a photon coming in and you end up with an electron and the photon being absorbed. You need something that the electron can collide with and get momentum. And that can be a phonon, a nucleus, an impurity, some. That's a general physics result. And in most cases, people in the literature so far have used empirical parameters or phenomenological parameters for this scattering time tau. They say, oh, here's the tau that fits experiments. But we're asking more and more of our calculations today. And so our goal in this lecture, in this school, and with this software project is to get tau entirely from theory, or to describe the physics of tau from theory. All right, so let's start first with how we describe absorption, optical absorption, or again, direct optical absorption in the linear regime. And the way we do this is we treat the electron-photon interaction as a perturbation. So our unperturbed state is the DFT wave functions, whether you choose to correct them with GW or not, and the eigenvalues. And the perturbation acting on the system now is the electron-photon Hamiltonian given by the vector potential that you see here. Okay, where A is the vector potential of the photon field. And V is you can use the momentum gauge or the velocity gauge. The velocity is more appropriate when we use pseudo potentials, and momentum. Both are accurate if you have actual potentials, the full Coulomb potential. But when you use pseudo potentials, the velocity is the right way to go. All right. So after we have the perturbation, we use Fermi's golden rule to find the recombination probability rate per unit time. So again, the transition rate from the initial to the final state is 2 pi over h bar, the constant free factor, the matrix element square, and times the delta function that conserves the energy. The energy of the initial state has to be equal to the energy of the final state. And that initial state is your electron stays in the valence band plus the photon coming in. Your final state, the photon is gone and your electron has been excited to a higher band. So the power that gets absorbed is equal to the energy of the photon coming in times the rate at which photons get absorbed. Okay, and that's what the equation means here. And so this is the power that gets absorbed by the material. We can also find, using optics, the power that is incident into the material if you have the given photon field. This is the incident power. And by simply taking the ratio between the two, we find the absorption coefficient. It is the energy absorbed per unit volume divided by the energy flux. That's what you see here. Okay. All right. So we do the math, we plug in our equations, and here's what we find. So the A fields cancel out, what you're left with is a factor of 2 for spin, 4 pi square, the charge square, the refractive index, the speed of light, and the frequency of your photon omega, 1 over the number of points you use to sample the Briggs zone, and the difference for occupation numbers here ensures that you go from an occupied state to an empty state. You know, if both states are empty, of course, you have an absorption. If both are occupied, you don't have absorption due to Pauli exclusion. And then here is the key quantity for optics, the velocity matrix elements, the matrix elements of the velocity operator between your initial and your final state, and projected onto the direction along which your photon is polarized. It can be X or Y or Z. You have plane polarization, cyclic polarization. That's how you quantify it here. And last, the energy conservation, the delta function, that your final state has to be your initial state plus the photon energy. Okay, so that's it. All of these quantities we can evaluate from DFT without even using phonons, because here we're talking about direct optics. Here are your GW eigenvalues, let's say. These are the velocity matrix elements between your states. All you have to do is just do this simple sum over the Briggs zone and the sum over bands. And how do now you go to the electric function, the imaginary part? Well, you have to multiply by the refractive index, the speed of light, and divide by omega, and you find a very similar equation. Just the prefactor is different, and that does not involve the refractive index here. So in practice, that's what we use in the calculations as the first step. So the equation you see here gives you the imaginary part of the electric function, and if you do the Kremes-Kronig relation, which relates the imaginary to the real part, you can find the real part as well. Okay, so again, it involves an integral over the Briggs zone, a sum over bands, and the quantities here again, velocity matrix elements and energies. Notice how for the real part, there is no delta function. Okay, there is no energy conservation here, which is a challenge because when it comes down to calculating absorption, you only need to consider electron and hole states within the window that your photon energy conserves energy. But for the real part, you see that for any given frequency omega, you need to sum over, in principle, all bands of your system. Even bands that are very high in energy can, in principle, contribute. So this is more challenging to converge. All right, so this is all this is well established when it comes to direct absorption, and it's available in codes like Berkeley GW or the Yambo code. It's very well distributed in the community. Now I want to tell you about the Phonon-assisted optics because that's one of the unique features of EPW. So to study Phonon-assisted optics in the way, there are two different approaches. The way I'll present here today is a second order perturbation theory approach, and Mario Zacharias will present the other method on Friday. So in the second order perturbation theory, we now treat our perturbation to be both Hamiltonians, both the electron-photon interaction we discussed earlier, in addition to the electron-phonon interaction that gives the momentum you need. And now to find the transition rate from the initial to the final state, now we have to use second order perturbation theory. So again, we have the 2 pi over h bar, the matrix element square, and the delta function for energy conservation, except now our matrix elements involves 2 steps, where you go from an initial state through the perturbation to some virtual intermediate state, and then from that virtual intermediate, you go to your final state, and you divide by the energy difference between the initial and the intermediate state. Now, because we're looking at phonon-assisted photon absorption, we keep only the cross terms here because the Hamiltonian is the sum of electron-photon plus electron-phonon. And so if you have you have 2 terms here, 2 terms here, you have 4 terms total. One of them is the two photon absorption, that is 2 phonon scattering, but the terms that are cross terms where it involves a photon and a phonon are the ones we keep here. So either you absorb or emit your phonon first and then absorb the photon, or you absorb the photon first and then the phonon. It's just a sequence of the 2 steps. Okay. So that's with second order perturbation theory. And once we plug in the equations for the electron-photon Hamiltonian, electron-phonon Hamiltonian, we arrive at this equation here for the absorption coefficient. Okay. Again, it looks a lot like the equation we saw earlier for the direct absorption. Again, a prefactor involves 4 pi square square, the refractive index and speed of light. We have some matrix element square, and we have a delta function for energy conservation. Now, some things have changed. Of course, the matrix element now is different. The matrix element now involves two steps, okay? And actually two terms. The two terms that you see here correspond to the two paths that you can take if you want to go from, say, an initial state in the valence band to a final state in the conduction band. For example, you either absorb the photon first, and then you absorb or emit the phonon. That's what you see with term S1. Or you have the electron-phonon interaction first, followed by the light absorption. Okay, that's the term S2. Okay, so in term S1, you have the velocity matrix elements at a K point, followed by electron-phonon coupling between K and Q. Or in term 2, you start from K, you go to Q, and then you have light absorption. Okay, and then you have to sum these two terms and then square, because each of them contributes indistinguishably, so you can't tell whether your light got absorbed along path S1 or S2. So quantum mechanics says we need to take the superposition of these two paths and then sum and then square the sum. Energy conservation again looks similar. The final state has to be the initial state plus the photon, plus minus the energy of the phonon that got absorbed or emitted along the way. Okay, and G that you see here is the electron-phonon coupling matrix elements that we've been seeing in the lectures of the school. Last but not least, we have the occupation numbers here. We need to ensure we go transition between occupied and empty states. And we also have that the occupation numbers, whether you absorb or emit a phonon, you take the right sign. So the upper sign for phonon emission and the lower sign for phonon absorption. So what's different here is that we do a sum over intermediate states M, and the intermediate states can be all states. They can be occupied, they can be empty. So even because here it's just a mathematical concept that we're using to expand the identity. So it's not used as it's not a real process. The electron never occupies that intermediate state M. So when you do sum over bands, even if they're occupied, even if it seems like you're evaluating Pauli exclusion, you're actually not. It's just a virtual process. And you also have to do this double sum over the initial wave vector of the electron and the final wave vector of the electron. And that's precisely where the challenge is. Okay, that's the challenge why a Phonon-assisted absorption has not been widely studied in our field, say, as opposed to direct absorption. Because in direct absorption, we have to do just a single sum over the Brillouin zone. Because for every electron K point in the Brillouin zone, the final state has the exact same wave vector. The photon does not carry much momentum, only 1% of the edge sides of the Brillouin zone or so. And so transitions are vertical. So you're just doing a single sum over the Brillouin zone. However, for Phonon-assisted absorption, you have to do this double sum. You need to take the initial state to be anywhere in the Brillouin zone, and the same for the final state. And that double sum is expensive. Not only because you have to do a Phonon calculation, the Phonon calculation itself is not very expensive. Doing one of the calculations is the time it takes to do, say, an SCF calculation. It's not too expensive. But the double sum is the expensive part, because if you need a good energy resolution for the spectra, you need to sample the Brillouin zone with a quite decent resolution, grids on the order of 24 by 24 by 24 or something, or even finer. So as a result, you end up with hundreds of millions of combinations between initial and final states. And that's the challenge. If you have to do this brute force, you can't do this even on the world's best supercomputers. And here's where the Wannier method becomes very important. So the trick here is to interpolate the electron-phonon coupling matrix elements and not to calculate them directly. So by using the methods developed by Marzari, Vanderbilt, and their team, we're able to transform from the Bloch basis to the Wannier basis. And that's what we use to interpolate the quasi-particle energies, whether it's from DFT or from GW, as well as the optical matrix elements. And that's what you need to do direct optics. But to do Phonon-assisted optics, we also need the tools that are in EPW, which are the tools to interpolate the electron-phonon coupling matrix elements in combination with the velocity matrix elements that we saw earlier. And the important thing is they have to be interpolated with the same phase to ensure that we don't have any arbitrariness here when we combine the processes. All right, so once we do that, then we can start getting results. Before I show you our results, I want to show you how the absorption for various materials depends on the photon energy. So experimentally, how do we know when we do an optical measurement how do we know whether the gap is direct or indirect? Because optical spectra, as you see, have tails. And the reason is that what we do is we do a so-called tau plot. Okay, so the tau plot is the following. We know from analytical equations that the absorption coefficient for direct absorption depends on the density of states, right, with respect to the direct gap. So it increases with the square root of the photon energy minus the gap and divide by omega. So if we take omega and move it to the left-hand side and take the square of the whole thing, we should find a straight line with respect to the direct band gap. Okay. Now for Phonon-assisted absorption, the same equation tells us that the absorption coefficient should be proportional to the photon energy minus the indirect gap, but not to the 1/2, but to the square power. So if we do the opposite here now, multiply by omega and raise to the 1/2 power, we should find a straight line. So that's what you see here. Let's say, look at the red spectra. It's the same spectra, except in one case, we multiply by the photon energy raised to the 1/2 power, or in the right-hand side, we raise to the square power. And what you see, the square power gives you, if you take the straight line segment, that will give you the direct band gap here. Well, if you look at the straight line segment from the 1/2 expression, you get the indirect band gap here, where they cross the x-axis. So that's why we measured experimentally. So do our theory spectra show the same? And the answer is yes. So this is our results we got back in 2012 for silicon. Here's the calculation of the absorption coefficient times h bar omega raised to the 1/2 powers to study the Phonon-assisted absorption. And as you see, we find these straight line segments. We get as a function of temperature. Each straight line here, the straight line here corresponds to the phonon emission term. This corresponds to the phonon absorption term. And as you see, as you increase the temperature, the phonon absorption becomes stronger and stronger. The phonon emission stays more temperature independent. But here you see those characteristic kinks and straight line segments near the indirect band gap of silicon. And I have to make a catch here that here we have shifted the energy onset by an amount of energy close to between 0.1 to 0.2 eV for two reasons. First of all, HW method has some uncertainty in calculating band gaps on the order of 0.1 eV, so that's a source of error. But also at the time we were not capturing the, we didn't put phonons in correcting the GW eigenvalues, so we did not capture the reduction of the band gap with increasing temperature that we heard from Zacharias and Giustino yesterday. Okay, but if you account for this rigid shift, which comes from the temperature dependence of the band gap, you see how the spectra are described pretty well for all these temperatures. And I also want to comment that, yeah, we did not include excitons here. It's a great question I've seen in the Q&A. We have not put excitons. Our hypothesis is that because the excitons are indirect, they have different momenta, the Coulomb effects between them would be weaker than, say, a direct exciton. And it turns out that because we see such a good agreement with the experiment, it kind of validates this hypothesis. But I agree with you. There's we did not include excitons in this calculation, but there was a recent work by Professor Giustino, Professor Zacharias at Boston University, where they did consider excitons and phonons in the spectra of germanium selenide. And I'll be happy to point you to it, or if in your organization can point to the reference, that'll be a great resource as well. So it can be done as well. You can combine phonon-assisted excitonic absorption as well. But we didn't include it here. It's not discussed in the form I'm presenting here today. So this is a spectrum near the onset. And as you can see, analytical equations work pretty well here. So in principle, you could find a decent band structure, you can find a decent matrix element that you could use to fit and reproduce experimental data in this region. But the power of the method is shown in this plot, actually, where the number of combinations of states that are involved in the visible part of the spectrum is vast. And there is no way that you can use analytical equations to describe the spectra here. Again, now we're looking at the energy region between the indirect and direct band gaps that covers the visible spectrum. And as you see, the agreement between theory and experiment is amazing, over several orders of magnitude. Again, I want to put the caveat here that we have shifted the onset because we didn't account for the temperature dependence of the band gap. But once you correct for this single number for each spectrum, you see how well it reproduces the experimental data. And so you see how many advances had to be made in the theory of the calculations and interpolation of Phonon-assisted phenomena. And this is the first calculation of Phonon-assisted optics of silicon in the year 2012, even though the experimental data at the time were more than 50 years old. But you see the power of what we can do today with the tools that we have in our availability, and we can go ahead and predict the spectra of new materials. Another topic where Phonon-assisted absorption is involved is in lasers, semiconductor lasers. And I'll tell you why. It's because they have free carriers. The reason we want lasers is to make projectors, both optical storage, laser projectors, and the goal is to develop green lasers so you can have a red, a green, and a blue laser that together you can make a screen even without needing bulky screens or LEDs or anything of the sort. And so to answer Ali's question in the chat, yes, in principle for any material now, you can calculate both the direct and the Phonon-assisted spectra entirely from theory. So we have the tools right now as part of the PW package. All right, so I want to go back to the discussion of the LED. So the way an LED works from a simplified point of view is the following. Here's your semiconductor chip, and you need an N-type region and a P-type region that you use to inject electrons and holes into a quantum well. We use InGaN as the quantum well because that's the best material that emits in the higher part of the visible spectrum, the blues, the greens, the violet colors. And by applying a battery, we take an electron from the valence band of the P-type material, move it along the circuit, and give it energy to put in the conduction band of the N-type material. Then the electrons and the holes get confined in the quantum well. The electron falls in energy by emitting phonons. The hole emits phonons that rise like a bubble also into the quantum well, or that they combine and give you photons. That's how the LED and the laser works. In the laser, though, in an LED, you want to get the light out as fast as possible, right before it gets absorbed anywhere else. You don't want any internal reflections or anything of this sort. In the laser, though, you do the following. The way it works is these materials are grown in layers. And what you do is you want to make an optical cavity along the horizontal direction. So at the interface between your material and air, that creates a mirror where the light bounces back and forth several times in order to get stimulate amplification of the light and get a laser lasing out along this direction of your stack. However, your photons do not live entirely in the quantum wells that get amplified. Instead, their optical mode profile, the electric field profile, extends into the P-type and N-type regions as well. And that's problematic because that's where light can get absorbed. Okay. So again, the equation for absorption in the Beer-Lambert law tells us that as the light propagates the material, it gets absorbed by electrons. Electrons get excited, the photon gets diminished. And as a result, the intensity decays exponentially as the light propagates the material. Okay, that's where absorption happens. But in the lasing medium, in the quantum well, after you apply the voltage, you end up with more electrons in the conduction band at the ground state, and here's you get amplification. So the first photon comes in, induces stimulated recombination, and the one photon becomes an identical clone of the first photon, same frequency, same phase, same direction. And as they propagate, they keep getting amplified. So in the end, you get your laser beam. And the competition between these two processes gives you your light output power. Okay, you want gain the quantum wells, but you don't want absorption in any surrounding region, surrounding materials. Okay, and that's where the free carriers matter. All right, so the surrounding materials have a band gap that is wider than the quantum well. So the layers that you see here don't absorb photons by, say, having an electron go from the valence to the conduction band. The gap is too wide. However, you have free electrons and free holes. And those electrons and holes can also absorb light, and they can take the energy to go to a higher state. That is called free carrier absorption, right? Those free carriers act like a metal, and metals are very good absorbers of light. They reflect a lot, but they also absorb a lot, any light that manages to penetrate into the metal. And so free carrier absorption is a potential source of loss in the material. In the case of gallium nitride, we see that direct absorption is actually weak. For holes, there's no states for electrons for holes to go to. For electrons, there is a band, but the transition is dipole forbidden. So you don't expect light to be absorbed by free carriers in a direct fashion. But once you put phonons, then you see that it becomes possible. Because now if you get extra momentum from a phonon, your electron can end up in states everywhere throughout the Brilliant Zone and for every photon energy. And that can be a source of loss in doped semiconductors. Okay. Long story short, here are the results for gallium nitride. The absorption probability is, of course, proportional to the number of free carriers that you have. So the more electrons that there are, the more absorbing the material will be. And the proportionality constant is called the absorption cross-section. Okay, it has units of area and magnitudes of this scale. So for 10 to the 19 carriers, let's say, that's typical for lasers under typical operating conditions, you find an absorption coefficient in the order of 10 inverse centimeter. So this absorption is much weaker compared to a direct cap material, right? It's 4 to 5 orders of magnitude weaker than, say, the absorption coefficient of gallium arsenide or halide perovskites or so. So it's a weak absorption, but remember, light has to travel back and forth many, many times. So it's a big source of loss. Ultimately, though, the problem is not free carriers. Just to wrap up this project and tell you how we're able to understand the loss in lasers, the problem was not so much the free carriers. Instead, the problem with gallium nitride is that the holes that are not free but are still bound to magnesium. The problem with gallium nitride is p-type doping is possible, but it's not very efficient. So the activation energy of acceptors in gallium nitride is 200 millieV. So you need to put a very high concentration of magnesium to get a modest concentration of holes. But what you end up with a very high concentration of holes here, still trapped to magnesium atoms. And this large concentration of non-ionized holes is what causes the loss. And that's been shown us experimentally, this prediction was verified experimentally, that indeed, as the photons propagate through the p-type material, they get absorbed by holes bound to magnesium, and that causes the loss in lasers. And it's still a factor, so we have to engineer photons to manage to avoid the p-type region as much as possible. So that's a direct implication of results that came from calculations. And this absorption by free carriers, this kind of absorption process also matters when we talk about transparent oxides. When we make electronics, like solar cells or displays, we really would like to use materials that can conduct electricity while being transparent. And that's a big challenge because commonly transparent materials like glass or are not conducting. So you can't use glass for that. And on the other hand, metals are great conductors, but they're not transparent. So the challenge is solved by looking at conducting oxides, namely such as tin oxide, indium oxide. These are oxides that are semiconducting, they can be doped and give you free carriers. So the conductivity is not coming from valence electrons, it's coming from the doped electrons. And because the band gap is so wide, you don't get absorption. However, those free electrons, in principle, can still absorb photon through the assistance of a phonon, and that can be a source of loss. In fact, it's a fundamental transparency limit in materials that are used for the applications. So what's the transparency limit? So did this work with Hartwig Pellars and a group of Chris van der Walle, and we found the fundamental limits to the optical transparency of these materials. For example, again, we find the absorption cross-section is a function of wavelength, and you see some trends. This is an exponentially, so it's a polynomial function of the wavelength, the third power of the photon wavelength. So this is a log scale, so a little bit confusing, but it's a log scale. So the slope you see here is the third power. And so it's much more important for long wavelengths. And you see, luckily, these materials are most transparent in the visible. That's what the absorption is there reduced. But that's the ultimate limit. And this is a limit we cannot overcome. If you have a doped material, you're going to have this absorption, and that's going to be a challenge when you design devices. I also want to show some results for silicon, because silicon is a very important ingredient in photonic circuits. So what's happening here is that earlier I told you about how electrons can transition from the valence band to the conduction band of silicon, but also if you have free electrons in silicon, they can also give you absorption. And in fact, they can cause loss in many different ways. One source, for example, is direct absorption. What you see here is process A. And here you see with a solid curve, right? This is possible because the optical transition is allowed. But also you have phonons that can give you absorption for many wavelengths. The direct transition, you see, it's like a peak. And because of the scale here, the peak appears broader on the right-hand side and the left-hand side, but this is a peak that we're used to seeing in optical spectra. But you also have Phonon-assisted absorption. All the scattering can come from impurities, from plasmons, and all of that. And last but not least, we also have the losses because electrons respond to electric fields the same way, like in electrical circuits, where an oscillating field creates an oscillating current, but the current moves to a resistive material, and you have some resistive loss and ohmic loss. And that's what you see here with the green curve. And if you sum all contributions together, Phonon-assisted, direct, and the plasmonic term, you see that we get results which are in excellent agreement with experiment over several orders of magnitude for all kinds of doping levels. So you see, you can also study how doped silicon can absorb photons, and that's also an important source of loss in silicon solar cells, as well as in silicon photonic circuits that are now being discussed in the context of photonics and telecommunications. All right, and of course, these processes also matter in plasmonic decay in metals. So this is not my work, this is the work of Anna Brown from Caltech from 2016. We can also use it to study the resistive loss and the plasmonic decay in metals, because the imaginary part of the electric function due to phonons also tells you about the lifetime of your plasmons and how you can use them to study plasmonic effects at the interface of metals and insulators. So another application where we can use these techniques that again involves electron-phonon coupling and optical transitions and the same physics that we discussed earlier in the previous slides. Now, I would like to highlight the alternative method by Wannier, Zacharias, and Giustino. Another technique what we'll discuss here is to do second-order perturbation theory, where we treat both the phonon and the photon as a perturbation. So we go to second-order perturbation theory. But the engineering of this method is that the method we present here, the Zacharias-Giustino method, is that the phonon perturbation gets embedded into your simulation cell. So you make a supercell and you displace the atom along a single optimal configuration. It's a linear combination of the various phonon modes. And then once the phonons gets embedded in your mean field theory, then you do a direct absorption, and you see how they also be able to get excellent results for the optical spectra of silicon, and the displacements again are needed in order to get the correct spectra in a direct regime. And it also gives you correction that in the direct part of the spectrum, where the second-order perturbation theory fails to describe the spectrum of silicon because it diverges, but also includes the correct physics for the temperature dependence of the eigenvalues and the Urbach tail. And for that, I will forward you to Marius' talk on Friday, as well as the recent publication that describes the techniques of the method. And so both techniques are complementary to each other. They both have their strengths. So both of them are well suitable to study the Phonon-assisted optical spectra of materials and identify new materials with desirable optical properties mediated by phonons. All right, and with that, I would like to share you some excellent references for the study of optics. In particular, the first two books, they're a pleasure to read. They're great introductions to the topics that I will discuss here, and some recent papers that highlight the results that you see here in this presentation. And with that, I would like to thank the collaborators for this project, because that's as you see, there are many people involved in this work. In particular, I'd like to introduce Zhao Zhang and Kyle Bushi from the University of Michigan, that you also have the opportunity to meet tomorrow at the hands-on exercises. And these are the two people working primarily in the development of the Phonon-assisted part of the EPW code. So I'll be happy to answer your questions and help you with any projects you may have in Phonon-assisted optics, as well as all the EPW collaborators that we work with to implement the Phonon-assisted part. As well as from Mr. Guang Shachi, who did the calculations for silicon, and other collaborators. And last but not least, I would like to invite your questions and like to thank you again for your attention. Thank you very much.
Thank you, Manos, for an excellent talk. So I think we have plenty of time for questions.
All right. Thank you.
Questions in Q&A, and I will interrupt if there are some questions like.
Fantastic. Sorry for that. Going back to slide 10, there's a question for slide 10. So let me see the question again. I apologize. both initial final wave function do not include the electron participation. Indeed, that is true. The states here are unperturbed. The mean field solution is the unperturbed totally perfect crystalline system. And we'll look at the effects of secondary perturbation theory. So if there's no polarons here, there's no perturbation to the crystal or to the states because of the electron-phonon interaction. All right. Another question for phonon perturbation using frozen phonons or supercells. One have only access to a few Q vectors, compared to the supercell. Indeed. Still recommend when you're perturbation the electronic part. I would say, yeah, the Wannier interpolation would be helpful, particularly if you want to use corrected eigenvalues, say from a method like GW that is corrects the bandgap and all. So indeed, that could be a useful aspect. Someone can still track specific Phonon-assisted transitions. Yeah, you could also to track specific phonons for the supercell method. I would say you may need to do some band unfolding to able to map them onto the phonons of the pristine cell. I would have to think exactly how to do this, but in general, I think it should be a do.
We lost Manos.
Manos, are you here? So I think we lost our speaker.
Can you guys hear me?
Yeah, Manos, yeah.
Okay, great, thankfully. I'm glad I had two devices open, thank you. Okay, all right, great. Fantastic. So, I'm sorry I lost the slides. I'll try to answer questions at least for the, so yeah, there are many, there are many pros and cons for the methods of, say, supercells versus the perturbation theory. I would say the perturbation theory, its big advantage perhaps is the data we got close to the onset of the Phonon-assisted absorption where only specific Q vectors are involved. Because that can be, you won't have to say calculate a supercell that is very large to capture those specific wave vectors. You can use perturbation theory. But supercell method is much more advantageous if you want to put also temperature dependence to the eigenvalues, as well as to capture everything simultaneously with one calculation, or perhaps even have flexibility on the functions that you use to do the calculation, because you can also use hybrid functionals, any kinds of corrections. As long as you can do optics, you can implement them with the supercell method.
Sorry, Manus, shall I say something also? Like,
okay, Marius, please. Sorry, yeah.
There is also there are some questions about supercells and perturbative approaches, and I think it would be nice if someone like sits down and write things like in the sense that which methods require lots of Q points and electron-phonon Wannier, like mobilities, cannot be captured with supercells, while some other observables can be done with supercells. So I think it would be very interesting.
Indeed.
Like
Indeed, that's a good point. Yeah. I agree with you. Usually, if your problem involves all phonon modes and the entire Brilliant zone, maybe it's better to go with the supercell, I think. While if your problem is more limited to a narrow region of bands, phonons, wave vectors, maybe it's better to go with the perturbation. What do you think, Marios?
I think I totally agree with you. Like if you try to do what Samuel is doing with for mobilities, I think it would be impossible to do with supercells. So we have another question from Walter.
Oh, please, yes.
Yes, very nice talk. I was wondering if you have any thoughts on applying these kind of methods to the inverse process of photoemission.
That's a great question. Well, thanks for joining, by the way. Yeah, we have looked at actually the process of phonon-assisted recombination in boron nitride, and it's actually boron nitride is an amazing material because even though its gap is indirect, the luminescence efficiency seems to be comparable or even better than direct gap materials. So there are materials for which the phonon-assisted luminescence can be equally strong or better than direct gap materials, and indeed that's something we would like to develop as well, especially for silicon, because even though the gap is indirect, radiative recombination, say, is not impossible. It is possible. Boron nitride is very strong as well. So indeed, it's something we would like to look at as well. And thanks for bringing it up. Yeah, that's something we would like to implement too. Yeah, and just again, follow up.
Yeah, so one other question related to that is, when you do your absorption, okay, so you have your matrix element modulo squared, and you have a sum inside your modulo squared over all the intermediate processes. But then in the end, you sum over all final and initial states. But I'm wondering if you do this in the luminescence and you have an exciton, say, formed from, if your exciton could be a coherent superposition of your final states, your conduction band states at your different valleys. And if then this needs to somehow be summed before you take the modulo squared. Have you thought about that?
Yeah, indeed, you would have to. Yeah, we have derived the equations for excitonic absorption, but you are right. One would first need to calculate the excitonic states, taking into account the Coulomb interaction between the valleys and electrons and holes, and also this need to be also finite momentum excitons, which are one more challenge to the theory. All of these kinds of actions can now be done, understand, with codes like Bertrand GW and Yambo. And yeah, once you express your excitonic function superpositions, then you have to go through intermediate states. A good question is whether intermediate states can be treated as excitonic states or free carrier states. I'm just brainstorming here. My inclination is to think that either would work, but one will have to do a calculation to try it out. But I agree with you. First, you have to find the excitonic states and then take the sums. Indeed, because those phases matter. Phases matter here.
Okay, thank you.
Thanks very much.
I think we can continue with Q&A from.
All right, great. A question in the silicon indirect absorption, why is there some difference between theory and experiment for high temperatures and low frequency? That's a good one. I think what we are not capturing with this method is the Urbach tail. That is how there's some broadening of the energy eigenvalues due to electron-phonon interaction. And I think that's something that Marius's method with supercells would be able to capture. And so indeed, that's a harder effect coming from phonons that should be doable. And also in different samples, different impurities may also cause this broadening. But my first suspicion would be the Urbach tail. And a question, is it correct that the kink near the indirect absorption cannot be captured by adiabatic methods? That I'm not sure. I think the kink that you see is one big reason is because you have phonon absorption assisted, one absorption assisted by phonon absorption and light absorption assisted by phonon emission. And those two have different onsets. They will differ by plus or minus the phonon frequency, right? And I think that's one source of the kink. So light phonon, if you absorb a phonon, you can have this absorption on lower photon energies, and then comes the phonon emission term, because your photon, part of the photon energy has to be used to excite the phonon. So I think that's a major source for the kink. Maybe it could be others, but I would like to follow up with you on this if there's a reference about the adiabatic methods.
So I think adiabatic methods should not be able to capture the kink.
Maybe it's a different kink that I'm referring to. So is there a reference for the Drude model absorption? Is there a reference for the Drude model absorption coefficient shown in the introductory page? Yes. So I think that maybe the first reference I shared on the slides, the Mark Fox optical properties, I think that would be a good reference perhaps to look at how free carriers are treated in the AC and the DC regimes. Question from Barbara. I'm assuming that absorption is calculated using all electron bands. Which electrons are used to calculate electron-phonon effect and absorption? So when it comes to the phonon properties, you only need the valence electrons because they only involve the charge density. But if you want to use electron-phonon coupling, you need the wave function for your initial and your final state. So in principle, you would need all the bands. And this sum of intermediate bands, that in principle would need to be converged. So we need to keep adding states in the immediate sum until your answer stops changing. But usually that converges much faster than, say, increases with 1 over the energy of those states squared. So it should converge pretty fast. And a question, second perturbation theory, one does not need to do a phonon calculation. You still need to do a phonon calculation for the matrix elements. So what happens is you have your initial state and your final state, and the intermediate state is a stepping stone to go from your initial to your final. But to go to the stepping stone, you need first a photon and then a phonon. And you can choose which one goes first. Both of them contribute. So either you absorb or emit a photon, followed by absorbing emission of a phonon. And so you would need this matrix element to find a probability for the whole process to happen. Oh, and there's a poster about uranium nitride from Barbara. Yeah, I'd love to come to your poster, Barbara, and learn about your work. A question about polaron jumping is a Phonon-assisted transition. How distinguish from ordinary Phonon-assisted transition? So the question here is, if you have, I'm trying to interpret the question, please correct me if I'm wrong. Is it how light gets absorbed by polarons? As opposed to a Phonon-assisted absorption, the two are related. So if I understand right, what I present today is you have a free Bloch electron, an extended state, that absorbs the phonons and transitions to another Bloch state with a different momentum, and subsequently you absorb the photon. In the case of polarons, you correct your starting point, right? You look at the interaction of electrons with the phonons, and you find a perturbed wave function, perturbed crystal in the presence of polarons. So that creates new states for electrons in the polaronic states. And then you can study optical transitions between these polaronic states. Is that your understanding? Is that your question? If that's your question, understand that here the spectra would be different. And for example, the energy of the polaron is less than the band gap, right? There is and that is seen in materials like gallium oxide, where although the gap is 4.5 to 4.8 electron volts, nobody has seen this energy as in luminescence. They see luminescence around 3 eV. That's more than 1 eV difference. And it has been attributed to the formation of a polaron. Once you excite the electron in the hole distorts the lattice around it to create a polaron, so it gets a new energy. And when the electron recombines with that hole, the photon energy that comes out is more than 1 eV less than the band gap. So this is different from Phonon-assisted optics, because Phonon-assisted optics still is near energies around the band gap, but phonons are also important in the polaron energies, in the formation of polarons and the spectra as well.
And I think more can be answered also in Feliciano's lecture, maybe for that. So I think, yeah, we have another question. No, we have no. So are there any other questions? Maybe oral questions? So I think we are done, and maybe we can have a break now. Am I right, Feliciano? And
I think we can shift the break so that we have a bit more time for the hands-on. Why not? Yeah.
I think we can reconvene in 15 minutes exactly, so that because we're a bit early. So we can close here and reconvene in exactly 15 minutes, if that's okay with everybody. Okay.
Okay.
All right. Thank you, everybody, for joining.
Thank you very much.